This is video number 55 on the foundations of arithmetic, algebra, and graphing with a focus on real-life interpretation and application. My name is Bill Kinney. It's part 14 of a subseries on algebra, formulas, functions, and graphing with an emphasis on spreadsheet usage. I'm hoping this might be the last video that I make in this series. And I'd like to make it kind of a fun video. I do reserve the right to make more videos if I change my mind here, but I'm hoping to make this kind of a fun video that focuses on some neat things that you can do with a spreadsheet and ultimately some neat things that you can do in math overall. And I also, in what I'm about to do here, want to show you the beginnings of some ideas from calculus. So first of all, we're going to look at a function here. The function is linear. It's y equals 5x. In fact, it's a direct proportionality. Y is directly proportional to x. And I'll go ahead and have Excel evaluate it like this. Equals 5 times B3 will be what goes here in cell C3 to take the inputs, the x values in column B, and give you outputs, y values in column C. And you should be able to predict what these are going to be. One kind of interesting thing you can do with functions is you can create another column here called first differences. And what I'm going to do in this column is for each one of these y values, I'm going to take it and subtract the preceding x value. And it might be better if we started here in the fourth row. So I'm going to take what's in cell C4 and subtract what's in cell C3. That's going to, of course, do 5 minus 0 here to give me 5, but then I'm going to copy and paste the formula downward, and so in the next place it's going to do equals C5 minus C4. 10 minus 5 is also 5, and then in the next one it'll do 15 minus 10, C6 minus C5 is also 5. All these first differences with this example are going to be 5, and that's because the function is linear. You'll always get constant first differences when the function is linear. You can create what are called second differences. You can do the same kind of thing with the first differences. Take this number and subtract the preceding number. These numbers, these first differences are all the same, so these second differences are all going to be 0. Okay? That's because the function is linear. What if I had a nonlinear function? X squared is a simple example. What's going to happen with the first and second differences then? So now I'll type the formula in like this. Equals B3 squared raised to the second power. 0 squared is 0. This time, now with x squared, the first differences are not constant, but the second differences are. Interesting. A different function gave you different first and second differences. Why aren't the first differences constant? It's because the graph of x squared is not only increasing, indicated by the fact that you've got positive first differences, but also concave up. If you graph this, you would see a concave up graph. The values of y go up, and they go up at a faster and faster rate. They jump from 0 to 1, then from 1 to 4 it goes up 3, then it goes up 5 to 9, then 7 to 16, then 9 to 25, then 11 to 36. That's what you see in these first differences. They go up. Though these first differences themselves are going up by a constant amount, 2 each time, 1, 3, 5, 7, 9, 11, 13, etc. That's why the second differences are all a bunch of 2's. The third differences can be done as well. Take the second differences and subtract each one from the preceding one. With x squared, the third differences are all 0. Kind of cool. Let's do another example. Y equals x cubed. Now I take my x's and I raise them to the third power. What's going to happen now? This function will be increasing and concave up. So you see first differences that are positive and increasing, but they are not going up at a constant rate. The first differences themselves would have a graph that's increasing and concave up. First you go up by 6, then 12, then 18, then 24, then 30. And that's what you see in the second differences. The second differences are linear. You go up by 6 each time, which is what you see in the third differences values. And then the fourth differences will be a bunch of zeros. I'm going fast, I know. You might want to re-watch this if you're feeling confused. It's kind of a neat thing to see. What will happen if I try an exponential function, like 2 to the x, which would represent a great interest rate of 100%? What's going to happen with the first, second, and third differences? The 2 to the x is also increasing in concave up. What happens? First differences are increasing at a greater and greater rate, the function values, and so are the first differences. And in fact, look at these. They match up. 8, 8, 16, 16, 32, 32. And look, the second differences match up as well. 8, 8, 8, and the third differences, and the fourth differences, and every difference thereafter. All these differences end up being functions that are increasing in concave up. That's kind of amazing. And that's a precursor of something that you would learn if you learn more about calculus. It's concave up in the extreme, if you will. I want to show you something similar to this, and also kind of neat. Have you ever heard of the Fibonacci numbers? We can study the Fibonacci numbers with Excel as well. If you haven't heard of the Fibonacci numbers, I'd encourage you to look them up. The first two Fibonacci numbers are both 1. 1 and a 1. The first Fibonacci number is a 1. The second Fibonacci number is a 1. What's the third Fibonacci number? Well, you find it by doing the sum of the preceding two Fibonacci numbers. 2. 1 plus 1 is 2. Now copy and paste that formula down. In other words, the fourth Fibonacci number is 3, which is 1 plus 2. The fifth Fibonacci number is 2 plus 3, which is 5. The sixth Fibonacci number is 3 plus 5, which is 8. You always add the preceding two Fibonacci numbers. The seventh Fibonacci number is 5 plus 8, which is 13. The eighth is 8 plus 13, which is 21. The ninth is 13 plus 21, which is 34. What if we did first and second differences with the Fibonacci numbers? Get a 0 there. But after that, you get the Fibonacci numbers again. Isn't that amazing? And if we did second differences, we'd get the Fibonacci numbers. Here's something else that's kind of interesting. If you take the ratio of successive Fibonacci numbers, 1 divided by 1, did you notice that? I did a division. C3 divided by C2. Copy and paste that formula down. You get numbers that, well, are always between 1 and 2, and in fact, interestingly enough, they seem to be settling down toward some specific number that's about that. That is a very special number in math. It's called the golden ratio. Golden ratio. And I'd encourage you to look that up too. That's an example of a limiting process. That's another calculus idea, as we're seeing a limit happening with this list of numbers here. Kind of neat. We can graph these things too. Won't take the time to do that. Before I show you one more thing, I do want to mention that you can use Excel to do, for example, irrational powers. Pi is an example of an irrational number, though it's stored as a rational number in Excel. This is just an approximation to 2 to the pi power. It's just one little thing I wanted to show you that you can do. To close things out, I'm going to show you something that's not in Excel. And you don't have to know this, but it's just kind of fun. It's something I'm proud I made. This is a program called Mathematica, And you can use Mathematica to do some really amazing things. And one of the things that I did recently through all this computer code that you see here is I made my own little planetary solar system. My own little solar system here. You see that yellow thing in the middle? That's my sun. And those two bluish dots, those are my two planets. They are orbiting my little toy solar system here, and we can watch them orbit. And all I want to emphasize here is that I had to use a lot of math to create this. And it is an accurate representation of the way planets go around stars. There's something called Kepler's laws that these toy planets are obeying, and that's just something else I would encourage you to look up. Math is involved in the real world, but it's also beautiful for its own sake, and I hope that came across in this video. Hi, I'm Bill Kinney, and while I'm not sure that anybody can truly be sure that they're really done with the video series, I think I might be here, and so I thought it would be good to take the opportunity to show you my face. I encourage you to keep learning math and other subjects in the future, and also just thank you for taking the time to watch this series. I hope that you got a lot out of it.